talking about LSTM networks today, try to understand them, and using this website or this blog, which I find it very interesting and good described actually. So you get first overview of recurrent networks, which is the over topic, and why it's not that good, and how LSTM, special kind of recurrent networks, actually solve this problem. What's the idea behind LSTM and how it actually works, or the steps that actually is behind or are behind the LSTM concept. Yeah, which I didn't understand so far, but yeah, I hope we will understand it together during this session. And different variants, which looks complicated in the first view, but let's see how good we come through this article and how good we can understand this. So, recurrent neural networks. I read this so far, and actually the idea of recurrent networks, or what's the main difference between recurrent neural networks and normal neural networks, is this loop. So normal neural networks doesn't have this loop, so they don't work with kind of information which is already can be taken to as kind of experience, which you can see here better in this picture. So with recurrent networks, which are these actually, or these, which is split it into these guys, they have also an input. So each one of these, I call them segments, I don't know how the author here called it, diagram, a chunk of neural network. Each one of them is actually a neural network, and they have an input and they have an output. And what's new here is that they actually do consider the input of the previous neural network element before them, which influence the modeling or algorithm here, and which influence also the output. And based on that, they also give the experience, I call it experience, now to the next element, and so on and so on. Problem is that if we have long-term dependencies, so it works really fine if the information or the previous information is not that far away from the actual element, like in this picture. So these elements, which are blue, have an influence on this output, but they're not that far away, so there's no problem. And one good example here is the, I think, language modeling. So if you just have these words, the clouds are in the, and you don't know the word sky, and the model tries to predict the word sky, it's really obvious because you have the word clouds here, and based on the structure of the sentence, you can conclude that sky is the the thing which is really fit in this gap. But what if it's getting more complex? So if this gap is a little bit much more, like you see here, and for example, they use this example: I grew up in France, I speak fluent French. So you won't come up to this idea that French is the right word in this case, or you wouldn't make the connection that the person grew up in France, so the sentence here requires the word French. The information is more complex, there are much more different possibilities, and also the context is, yeah, the context is not that clear and may also be a little bit, they're not that close together, if I can say so. So it's, that's the limit of RNNs or recurrent neural networks. So they're first introduced in the 90s. Whoa. And LSTMs, long short-term memory networks, are a special kind of RNNs. So they're able to do this kind of, or are able to deal with this kind of problematic or problem. First introduced in 1997, which is, well, okay. And yeah, they are used for, yeah, interesting to know when or why we use LSTM. How I understand it from this article, they are very popular now. And one example is mentioned before, translation, everything was language, I guess. Everything, prediction of time, things where you need the previous information or time things. I don't know, one example where I got this page was yeah, the prediction of the stock market. So actually the actual value of the stock market depends on, or it may be good to know what happens before and have this kind of experience so that you don't start from zero if you want to, I don't know, predict the stock market price for some stocks for the next day. So in these cases, it makes sense to have to adapt this kind of experience to the network. So based on that, that it can work properly. So now that's the part I understood so far, and now let's read together the next following chapters. They work tremendously well actually. Okay, they are, like I mentioned before, they are designed to avoid long-term dependency problems like this one. Yeah. They remember information for long periods of time. Okay, that's their structure. The structure of RNN. So you have neural network, and a neural network, which are basically one by one to each other and are connected. That's why they use this form of chain. And the structure of LSTM you can see here. They also have this chain-like structure, but the repeating one has a different structure. Okay, what does that mean? Instead of single neural network layer, I don't know if they just mean this, but I'm not sure if he means that with the neural network layer, because that is actually an activation function, but I'm not sure. They are four interacting in a very specific way, so I think that he really means the activation function. So you have here four different things which are connected somehow, and yeah, do this output thing, and this just has one. So yeah, yellow neural network layer, which is the term here. Vector transfer, don't know what that means. Copy, don't see any copy here, and I also don't see the concatenate. Step by step, okay. In the above diagram, each line carries an untyped vector from the output of one node to the input of the others. The pink circle, remember, blah blah blah, while the yellow boxes are learned neural networks layers. I don't know what actually he means with that. Yeah, but let's assume that this is just one normal neural network layer so far. Lines merging denote connections, while a line forking denote. What's forking? Okay, understand. Okay, maybe I translate this one. Don't get it so far. Okay, they just explain the symbols, but I don't see it here. But yeah. Let's get to the next steps. The core idea behind LSTM. Now it's getting interesting. The key to LSTM is the cell state. What is that? The cell state. The cell state, the horizontal line running through the top of the diagram. So this thing is called the cell state. Have something like, yeah, I guess the cell state is CT, and the cell state of the previous element, I guess. Cell state is kind of like a conveyor belt. Okay. Okay. It runs straight down to the entire chain. The entire chain. So you can see it here, I guess. And with only some minor linear interactions. Okay. Very easy for information to just flow along it unchanged. Okay. I guess this is this thing that flows through all these elements. I would say this is something like the memory or the experience of the whole LSTM network. Okay, the LSTM does have the ability to remove or add information to the cell state. Okay, regulated by so-called gates. Okay, so each element contains gates which you're able to remove or add information. So actually you change your cell state, or from my intuition, or if I use an analogy here, I would say you change your experience based on what you're experiencing right now. Okay, here they explain what gates actually are. So gates are okay. Oh, wait a second. There's some kind of lag. I don't know why. But yes. To optionally let information through, they are composed out of a sigma neural net layer. Okay, so this is a gate, multiplication operation. This is also a gate, and this is also a gate. Go back to this picture. So there are 3 gates, okay, at each element. Let's see what they do. Sigma layer, this thing, outputs numbers between 0 and 1, describing how much of each component should we get let through. Okay, 0 nothing let through, 1 everything let through. Okay, so this is the guy who decides if you come into the cell state or not, if I can explain it like that. Okay, LCM has 3 gates. These, no, these, and this, to protect and control the cell state. Okay, very interesting. Now it's getting to the, now we're getting more in detail. Step by step, LSTM walkthrough, which, yes, should be interesting now. Whoa, what's that? Okay. The first step in our LSTM is to decide what information we're going to throw away from the cell state. Okay, it's made by sigmoid layer. Sigmoid layer called the forget gate layer. Okay, it looks at ht minus 1. ht minus 1, I think, is the thing from Yeah, what is actually HT? Don't explain it yet. Oh, I didn't see it. But something from the element before that. So it looks at HT minus 1 and XT. XT is the input of this actual element. And outputs a number between 1 and 0. Okay, so the sigmoid, the output of the sigmoid, or what the sigmoid does is take this information and get out a value between 0 and 1. 1, everything goes through. 0, nothing goes through. Everything's blocked. So take these two values. For each number in the cells, it looks at it and outputs a number for each number. For each number in the cell state CT1, what does that mean? And outputs a number for each number. Okay. Are they multiplied, or how should I interpret this multiplication operation? Okay. Represents completely, keep this. Okay, so they take this, these sides of 0, 1, take this together and something they, is that right? Or what is the connection? A 1 represents completely, does that mean that is that the connection to this sigmoid layer, or is that the connection to this multiplication operation? This is, read again, we want to throw away. Okay, looks at an output somewhere would wait for each number in the cell state. So the cell state actually just state, and for each of these states you decide if it's 0 or 1 based on this part. So this part does nothing, it just contains all the states or the information of the previous thing, and this thing does the calculation and decides if it's 1 or 0 or something between that, and actually decide what to forget and what to contain. Yeah, based on the thing before and the thing new input now. Okay, let's go back to our example of language model. Yeah, example is good. Trying to predict the next word based on all the previous ones. Okay. In such a problem, the cell state may include the gender of the present subject so that the correct one can be used. When we see a new subject, we won't forget the gender of the old subject. Okay, makes sense because it's irrelevant now. So this decides what is irrelevant, what we should forget. Sigmoid contains of thing weights of the forgetting gate layer multiplied with whatever. Is that a vector? I don't know. Plus a bias. Okay. Check. So the forgetting gate. Next step is to decide what new information we're going to store in the cell state. Okay, now we're going to the store part. Forget part, store part. This has two parts. First, a sigmoid layer called the input gate layer. This guy, I think. Decides which values we update. Okay. So, I think they get, do they get these two or just the input? I don't know, but yes, they go through this again and decide what's IT. Okay, the new information is maybe IT. Yeah, IT is maybe this one. Yeah, maybe. Yeah, let's assume this. IT is maybe the input gate layer, decides which values will update. Okay, so which of these get an update with this new input information? Next, a 10 layer, this guy, creates a vector of new candidate values, CT thing, that could be added to the state. New candidate values, what are these guys? Okay, it doesn't explain. In the next step, we combine these two to create an update to the state. I would wonder what this actually is doing. So this channel layer creates these, but so you create new possible candidates. Let's look back what are actually candidates. Candidates for the cell state. So actually you create new cell states, possible new cell states? I don't know. So if we keep this example with the language thing, maybe each candidate is each word of a sentence, maybe. And then you decide which word of the sentence may be important or not, and you forget it in the forget layer. And you continue the sentence with the new words and decide which of these new words you just in your line have an influence on the understanding of the whole meaning, which I think the whole meaning or the meaning in general or the experience is represented by the cell state. Not the cell state. The cell state is just one thing, I guess, but I mean this whole line here. That's how I imagine it or how I understand it so far. Okay, so with this layer you decide which one to update. The input gate layer. Which values we update. Okay. Yeah, I have a kind of feeling for that, but actually I don't get it really so far. But yeah, we have an example here, I guess. In the next, we combine those to create a update of the state. Okay, this is the forget gate, and this is somehow the update gate, and how that actually works. Yeah, maybe it gets clear with the example. In the example, we want to add the gender of the new subject to the cell state to replace the old one we forget. So this gender of the new subject, so we forget the old subject because it's not relevant anymore. That's decided in this thing. And we get a new subject based on the new input, or we get it from the new input. And we need the information of the gender of this thing, or we want to add this information of this new information we really want to add to our understanding or experience or whatever you call this line to be able to get the meaning of the whole sentence. So this is done by this thing. Yeah, but I actually don't understand so far the difference really between these. So this, the left thing is the input gate layer. Decides which values we update. So it's decided that we update the gender because the old gender is not relevant anymore. Creates a vector of new candidates. Actually, wonder what it might be. Maybe they changed the subject because you got a new subject, you change new candidates, you have a new subject. Based on this subject, you have a new gender, and the left part decides if this new information that you really get a new gender, if that's relevant for your understanding. Okay, I think now that makes somehow sense. If we keep this language model example in mind, that's how I can, yeah, it's how I think it works. Okay, it's now time to update the old cell state CT-1, this guy, into the new cell state CT. Previous step already decided what to do, we just need to actually do it, okay? We multiply the old state by ft, forgetting the things we decided to forget earlier, okay? With this multiplication, okay, multiplication with CT1 actually does the forgetting, yeah, okay. Okay, so this thing here under tells you what to do, and if you multiplied it with the old state, it actually does that. That's how I understand it. Then we add it minus ct multiplied with ct, this thing. This is the new candidate value scaled by how much we decided to update each state value. Okay, new candidate values, new subject in this case, and yeah, these, they all have different states, gender, for example, and we decide how much important it is actually to take the gender, for example, into consideration. So, language model, the example. We drop the information about the old subject's gender and add the new information we set to this stage. Okay, that's, this part actually does that. And yeah, we have an updated state, I guess, how you would say that, updated state, and based on this state you can actually predict or use that language model. Okay, finally we need to decide what we're going to output. This output will be based on our cell states, this guy, but will be a filtered version. Okay, let's see how they do that, or what they filter. First we run a sigma layer which decides what parts of the cell states we're going to output. This again? Okay. I think these two again run through sigmoid. They always run through sigmoid somehow. Okay. Yeah, but I guess they have all different weights, so they are all different kind of neural networks. It's mentioned above here somehow where that it's not just a normal neural network, it's, yeah, instead of having a single neural network layer, therefore, okay, it's a layer, actually, they are layers. This thing is neural network and these are the different layers. Yeah, makes sense. So I think each layer has its own activation function. I don't know. Yeah, not sure, but actually these are the layers. So what does the last layer do? This will be better, but we will filter version. Filters the information. First run a sigma layer, which is like what part of the cell state we're going to output. Then we put the cell state through 10. What part of the cell state we're going to output? Okay. Then we put it through 10 to push the values to, okay. Yeah, I don't know why we need this, but okay. And multiply it by the output of sigma gate. Well, so this cell state experiencing goes through this 10 layer, or it's not a layer. Yeah, maybe it's a layer. I don't know. Multiplied with this sigmoid thing, so that we only output the parts we decided to. They are both HT. They are both HT. Okay. Yeah, okay, HT is the output. Yeah, HT is the output. Okay. Damn. So this thing was the whole time the output, and I didn't know it. Okay. Now makes sense. So you see the output goes here as output, and the output is used here again. It's the same for the next layer, for the next element thing. Yeah. Can't tell it before that, or I could read more carefully. So always take the output before and the actual input now. Goes through sigmoid, goes through 10, so these guys combined with the cell state together, and they give the filtered version, which is the new output. Is that right? Then we put the cell state through 10, okay, and multiply it with the output, so that we only output the path we decided to. Where actually comes this decision from the forgetting gate, from the update gate, which has an influence on the cell state. Cell state goes somehow through this 10 thing. Why? Yeah, I don't know why, but it does that. And based on that, they somehow multiplied it again with this thing. I don't know why too, because they already use it in these cases, but okay. That's how they actually create the output. And that's a gate too, yeah, because it had a X or multiplication symbol. Bayesian sentence, okay. Filtered version, still don't know what that means. Okay, variance. What I've described before is pretty normal, but not as the same as the above. In fact, it seems like most every paper I use slightly different version. The difference is minor, okay. One popular in 2000 people connections. That means that we let the gate layers look at the cell state. What does that mean? The gate layer, the gate layer, the gate layer? What's the gate layer? And the gate layers. So this thing, because here's the X, so the layer before that is this thing, this layer before is that thing, the layer before that is that thing. Look at the cell state. 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 Okay. If I look at this, it doesn't have this connection. So this thing is new. This thing is new. So you have this cell state. And this thing is new. But they are all different. So these first two gates have the, yeah, I think it's right. So these two things, forgetting and updating layers, have this information of the old, how do they call it again? Cell state, of the old cell state, while the last layer, where you actually have your input, needs the information after these, after the workout. I don't know how to call that, but yeah, let's call it workout. The workout of the two previous gates before. Okay, and they take this into consideration. I don't know. Yeah, if you take this into consideration, maybe it's better, but yeah, I would really want to know when you actually need this, or what the real benefits are behind this idea. Peoples, called peoples, people connection, where you can look, okay. Many peoples will give some peoples and not others, okay. Another variation is the use of coupled forget and input gates. Coupled, okay. Instead of separate deciding what to okay, we should add, what we should add new information, we make those decisions together. Okay, so you don't forget first and then decide what to update later, you do it together. We only forget when we're going to input something in its place. Okay, makes sense. We only input new values to the state when we forget something older. Okay, makes sense. And what's the difference? If you look at this standard version and this new thing, -1. -1 to this one. Yeah, so if you forget A, you have, yeah, I don't know what the -1 means, but if you lose an A, you have to add an A. That's how I would interpret this picture. A slightly more dramatic variation on LSTM is the gated recurrent unit, or GRU. GRU, introduced by Cho in 2014. It combines a forget and input gates into a single update gate. Wow, what's that? What does it do? A gated recurrent unit. I don't even know what that means. Alright. So it's close and comes again if I would translate these three words. Combines the forget and input gates. Forget and input gates, this thing, into a single update gate. Single update gate. So you merge forget and input, or how should I understand it? It also merges, let's continue. It also merges the cell state and hidden state. Whatever the merges, it merges the cell state, and the hidden state, whatever it is, and makes some other changes. The resulting model is simpler than the standard and has a growing increasingly popular. Okay, and I think this paragraph doesn't describe it further. Let's have a look again what's different. Unfortunately, it's here above, but if we look at this, the standard version is like this without the -1. Let's keep that in mind and then compare these two. Wow, totally looks different. Oh gosh, where's CT? So you have to forget. Where's the forgetting layer? Okay, the only thing that no is completely different. Gosh, RT. Okay, if I just look at the picture, I really don't get it. Combines the forget and input gates to a single update. So you have these. Actually, I want to know what's the input gate. The input gates. No, that means these two. The forget and input gates. What? This is the forget gate, but what's the input gate? This thing? Maybe. Input. Input. Okay. Because that's the update gate. You combine these two into a single update gate. So the old update gate isn't there anymore. How should I interpret this? No, it's still there. It's this thing, and it's still there. The old input update gate, sorry. But why do they combine it together and have another update gate? So do they have two update gates? Okay. Also merges the cell state and the hidden state. What is again the hidden state? Hidden state. What is that? I don't know. It makes some other changes. The resulting model is simpler than standard. Okay. It's simpler. Yeah. I don't click on this, I think. Okay, let's click on this. Joe, what did you do? Whoa, 15 pages. Okay, I don't think I will understand it in new architecture, evaluation, score, blah blah. Yeah, that's why they are so cool, and yeah, why it's working. But how does it work? The post able to score, but okay, with new architecture, okay, I think somewhat before that. That's results, I guess, but the idea is not in 4. Maybe in 3, maybe in 2, into RNNs, encoder decoder. Whoa, I don't know what that is. Yeah, I think I don't get it. Number that has learned to encode a variable length sequence into fixed length vector. Okay, don't know what that means. Hidden unit remembers and forget. A hidden unit, yeah, that's our hidden unit. Whoa, I have to understand this whole paragraph. What's a professional hidden unit? F in equitation 1. Hidden state HT. I thought HT was the output. Dude, what's this? Oh, or it's maybe this new HT with the symbol is the hidden layer. This cell state with the hidden state. Yeah, but even if that's a hidden state, I actually wonder what it actually does. What's the idea behind this? Don't know. Don't know. Hidden state HT. What does it do? Because the fixed length vector on the code different sections. Oh no, wrong path, sorry. Type of hidden unit that has been motivated by the SAU but is much simpler to compute and implement. Okay. The update gate Z selects whether the hidden state is to be updated with the new hidden state. The new hidden state. Whether what? So Z is closed, so this thing is okay, not closed. Okay, it depends on R. We set gate whether the previous hidden state. Bro, where's the output? Update gate Z selects whether the hidden state is to be updated with the new hidden state. Okay, I think this is the result, and if this makes the click to the right, this thing goes here, I guess. But it's not a circle. Okay, what's R? The reset gate R decides whether the previous hidden state is ignored. The previous hidden state, where does that come from? So if it's in, it's resetted. And this thing is closed, and I don't get the idea. X is the output. Go in. Yeah, maybe I don't need a circle. Maybe. So if it's not resetted, I assume now, and input goes through this, and if this is closed, it goes through that. And I still don't get the idea of the hidden layer. What does that do? Why do you need a hidden state? Good. As the function of remembering and forgetting, which is merged like this guy here mentioned before, but okay. Yeah. I don't get it. I'm too dumb for this. But back to normal life. Okay, forget an input. Okay. Okay, I don't understand it so far and don't get the idea why it's, if it's an improvement, why it's, if it's so, why it's an improvement, when and in which cases is better than the normal LSTM. What's the idea to modify it like that? I don't get it, but yeah, maybe I have to read that whole paper to understand it. What Cho et al. Does. Okay, let's continue. These are only a few of the most, okay, there are a lot of others. Okay. Okay. Oh, that's a good question. Which of these variants is the best? Do a nice comparison. Popular variant, but they are about the same. That's good. There are more than 1,000 RNN architectures. Also, RNN, not LSTM, sorry. It's finding some that work better than LSTM or certain tasks. Okay. So, like always, there's no free lunch, as usual. Oh, conclusion. I love conclusions. People are achieving with RNNs. Essentially, all of these, okay, a lot better. LSTMs are a lot better than simple RNNs. Hopefully, okay. Yeah, I think we get an idea of how LSTM works. It's natural one. Is there another big step? Okay, that's more an outlook. Common opinion 1-0. Yes, of course. Researchers. Yes, this always. And if not, we have to write yes. There's the next step, and it's attention. Attention. Okay. The idea to let every step of the RNN pick information. Every step pick information to look at from some larger collection of information. So like looking at itself and making itself the connections somehow. For example, if you're using an RNN to create a caption describing an image, it might pick a part of the image to look at every word it outputs. Okay. So like let the network decides which part of the information to look at, which parts to focus more on, or which parts to consider which the human doesn't consider naturally. Maybe that. Give the network the idea on which parts to focus on and what to pay attention to. Maybe it's that. Okay, I just read that. In fact, chew it all. It might be a fun starting point if you want to explore. Okay. There's been a number of really exciting. Okay. Attention isn't the only exciting thing. For example, grid LSTMs. What that exactly is, I don't know. Doesn't describe it. Work using generative search. Okay. What are generative models? Generative. I'm sure I pronounced it wrong. But okay. Okay. Yeah. So really interesting article. Yeah, sum it up. Recurrent neural networks works with has some kind of memory because it takes the output from the previous one to the next one. Has its limits if the distance between now and before is too great, or I don't know if it's always like that, or if the complexity is too high. I don't know if that's really the distance, just the distance, or also means the complexity. We have problems. LSTM works with these problems. So RNN structure, LSTM structure, RNN structure. So each one of these green things are neural networks. Just has a layer. These LSTM structures has 4 layers, which the idea is on this called cell state, you have your kind of, it's kind of your experience or the meaning in general if we keep this language example. So I think this is a good example. So the ability to get the meaning of the sentence is here. And there, yeah, you have gates to decide which information to add in or which information left out to form your new experience, or actually to decide if you go further in a sentence. I don't know if really if you want to translate a sentence, if you go element by element, or if you do it the other way around, because think you have to look first at the whole sentence somehow and not go each word by word from left to right. And yeah, so decide and how you decide what to put into this cell state, they call it cell state, and what to forget is here, or is adjusted by so-called gates. First gate is the forgetting gate, second gate is the update gate. So forgetting gate, you decide what information is not important to you anymore. For example, if you have this, it will keep this language example. So if you uh, have a new sentence and you have a new subject, this subject is more relevant now. And the gender of the old subject is not relevant now because we don't need the subject anymore. So we don't need this gender of this subject for further understanding or further conjugation, or not conjugation, but the other thing. I don't know, if you use an adjective, you need the gender for specific languages, not English, but yeah. So with this information, you decide what to forget. In this case, the gender. You have to forget the gender of the old subject, and also decide what to update. So based on the new input, you have a new input and a new word, for example, and this is a new subject, and you decide, okay, I have a new subject. The network decides I need gender. Boom. Input your update your your experience thing here, or for getting the whole meaning, you have to update. You need information of the gender of the new input element, which is the new subject, which is the new word. And yeah, actually this thing here, you use the old state, do this multiplication stuff, and you get, boom, your new CT, your new cell state. And based on this cell state, you go to different layers again, and I don't know actually how that works, but actually you get a new output. So transform your CT, your cell state, to something like an output. I guess, I hope I explained it right, and that I hope I don't mix up things. Here, 10 layer, I'll go to sigmoid gate. Yeah, it's so right. I still don't get what the sigmoid gate here actually does. Yeah, yeah, okay. Maybe again how strong the actual information and the previous information goes into consideration of the current cell state. The current cell state we build up, or the decisions how to transform the cell state we already did here. And these are combined together, and you get a new output. Different variants. Yeah, just think the author of this article just wanted to show what is possible, and that there is not only one LSTM network, there are many combinations of this. And yeah, they are still a very interesting research topic. Yeah, and this idea of the attention map is really interesting. So let the network decides where to focus on this whole thing of information. I don't know, the whole sentence. Or he uses the example of a sentence or a caption in an image. Do you need the image? Does the image give you information how to interpret the sentence, so that you just don't look at the sentence and try to get the meaning of just the sentence, but also use other information of the picture in this example. So actually tell the network how should it actually, at what stuff should it put its attention to, where, what is necessary or what gives me more value if I consider other types of information which is not um, clearly, so that the network is able to learn this and use it for the advantage of the modeling. Yeah, all in all, very interesting article. Hope you get yeah, an idea how LSTM networks works now. Yeah, thanks for watching and see you soon.